Okay, this is chapter on states of matter, video 2. Okay, now what I'll do is I will repeat what I went over at the end of video 1. Okay, you ready? Okay, what I want to do is I want to get you used to where does pascals come from and where does 101.3 kilopascals come from for an atmosphere. What is all that about? Okay? Now, joules, a joule is a kilogram meter squared per second squared, right? A Newton is a kilogram meter per second squared, correct? Right. Well, do you have the feeling that pascals might be something? Yeah. Well, a pascal is a 1 Newton per square meter, right, is going to be a pascal. We know that pressure equals force over area. That's what pressure is, force per unit area. Okay? Are you okay with that? Okay. Now, let's take a box. And I think we did this last time on Sunday, but let's take a box. Is anybody cold in here?
Yes. No.
Yes.
Okay. Somebody turn that on at some point, and it's really cold. Please don't turn the AC on unless you ask me, because everybody suffers as a result of that. So 1 cubic meter. So 1 cubic meter of water, okay? 1 cubic meter of water is 1,000 kilograms. It's 1 cubic meter of water, 1,000 kilograms. Now, that's 2.2 pounds per what? Per kilogram. So that's 2,200 pounds or 1 metric ton. That's 1 metric ton. So it's a lot, okay, of water, correct? Now, the density of mercury is 13.6, correct? Yes? And an atmosphere is 76 centimeters, correct? Of mercury, correct? What is 76, what is, and one atmosphere of mercury is 0.76 meters, right? 0.76 meters, which is 76 centimeters, which is 760 millimeters. Same thing, right? Yes or no? What is 0.76 times 13.6?
It's 37.5.
No. 0.76 times 13.6.
10.336.
10.336. So we rounded with 13.6, so it's around 10. Is that okay? Can we agree that it's 10-ish?
Yeah.
Is that okay? 10-ish? Okay, good. Now, all right, good. Now, what is, this is 1,000 kilograms, correct? That's 1 box, 1 cubic meter of water, correct? Now, you know what force is. Force is mass times acceleration, right? And if it's a weight, it's a vertical force. That's a weight, right? So it's going to be mass times the acceleration due to gravity, correct? Right? What's the acceleration due to gravity rounded to 1's place? 10 meters per second squared, right? So what is MA? Mass times acceleration. MA. Mass times acceleration. Mass 1,000 kilograms. Mass in kilograms times acceleration, meters per second squared, rounded 10 meters per second squared. What is 1,000 kilograms times 10 meters per second squared?
10.333.
10,000. Where do you get 10.333? That's okay. He's a little sleepy. That's okay. I'm almost done. Okay, you look a little tired. All right. So 1,000 times 10 is 10,000. What are the unit labels?
Kilograms.
No, kilograms times meters per second squared is kilogram meters per second squared, or a Newton. No, not joules. Joules are kilogram meters squared per second squared. They're losing their minds. Overload. Okay, so it's going to be 10,000 newtons, right?
Yeah.
Right? And what's the area of the bottom of this tank?
1 meter.
1 meter squared, right? I didn't say what's the volume of that 1 cubic meter. 1 cubic meter. What is the area of the bottom of that 1 cubic meter?
1 meter.
1 square meter. So it's going to be 10,000 newtons per square meter, correct?
Yes.
Is that right? Okay, now. Would that, if you were underneath that, would that be really heavy?
No. Yes.
It wouldn't be?
Yes.
Mustafa? I'm going to put
Wait, under the box or inside?
under the box. I'm going to put you under this box. Under this rigid box. You know what they would call you after you were under this rigid box?
Pancake.
They'd call you pancake. Okay. They'd call you Little Mustafa. Okay?
Already called me.
They call him very little Mustafa. Okay. Now, if they put you under, you would be very little Ishmael. Okay? Okay.
Very.
It would be very difficult, but we will make very little Ishmael. Okay. Very good. Okay.
Pancake.
Now, you're a hog, right? Are you a hog? Are you a guard in football? Don't you play football?
Yeah, no, I'm
Are-
a center.
Oh, you're a center.
Yeah.
Same thing, really. It's kind of a guard. So you're a hog. You're a kind hog. That's a nickname for guards in American football. They're called hogs. And the expression is you're a kind hog. It means you're a nice guy. Okay, good. He thought I was like making fun of him, you know, like, oh my God, he called me a pig, you know. Called you a hog. Hogs are, it's a good thing. Okay, all right. Now, so, let's say Mustafa didn't feel any pain. You put a giant box on top of him. He's cool. Okay, now, let's put 9 more on top of him and see how he feels.
If there was zero atmosphere,
You're going to be called very little. I mean,
Minimal stuff.
stain on the rug. Okay? Now, so you would have 10 boxes on top of you, right? You would have, what would be the total amount of force?
atmospheric pressure.
What would be the total amount of force?
1.3.
Well, no, what would be it would be 100,000 newtons, right?
Yes.
Right? Okay. And what's the area?
1 meter squared.
1 meter squared. So what's the pressure?
1 Pascal.
No, not 1 Pascal.
101.5 kilopascal.
No, well, yes, ish. It would be. They're not letting me off the hook, Abby, are they? They're like, you know, trying to ruin my lesson here. You know what I mean? I'm being attacked.
1
Okay.
atmosphere.
Yeah, it would be 1 atmosphere, exactly. Because what did you say 13.6 times 0.76 was?
10 point something.
10.10-ish. Didn't you say 10-ish? 10 meters-ish?
Yeah.
That's what the height of this is, 10 meters.
10-ish.
So that's one atmosphere. So you're on the bottom of this atmosphere, but you don't really feel anything. So Mustafa, you should have said, I'm really cool. They call me M, maybe. They call me Mustafa. I am like cool, I'm chilling. You are on the bottom of a column of air that has a weight of 100,000 newtons and a pressure of 100,000 newtons per square meter. So Mustafa, you should have said, I will feel fine.
But that's only if atmosphere was 0, which it's not. Atmosphere is 1. So if
He's
you put
arguing
that
with
on
me.
top of
He's arguing with me.
If you put that on top of me with the atmosphere, that's
No, that would be 200,000. Yeah, if you put, in other words, you have 100,000 on you now. If you put an additional 100,000, yes. But the point is this. The point is this, and everybody finds this amazing. But that column of air that's very tall, and we'll do that column in terms of the density of air Thursday, but that column of air is very heavy. but we don't feel it because we're used to, essentially, wave my hands, very simple answer is we're used to it, essentially. So, now, so F equals mg, F equals km per s squared. F is 1 kilogram per times 10 meters per second squared. That's 10 newtons. So that's what a newton is to review. F equals ma, 1,000 times 10 meters per second is going to be 10,000 newtons, right? This was going to be 100,000 newtons. 1 newton per meter squared is 1 Pascal. So the atmospheric pressure is 100,000 pascals-ish. So it would be 10.13. So if you actually looked up the real density of mercury and didn't round it off, you would get something closer to 10.13. The actual, in terms of force significant figures for the atmospheric pressure is 101.3. Is that correct? Yes or no?
Yes.
Right. Somebody for the time being here, Pablo, look up the density, the actual density. I want at least 4, maybe 5, 6 if we're lucky, significant figures for the density of mercury. I want you to look that up, raise your hand when you're there. I want to go on to the next point. Okay, I only got like 15 minutes left. Okay, so I want to do this. Yes? Are we all right with that so far? It's going to be on video so you can review the lesson. Okay? Now, so we've done this, 10 meters squared tall. All right, now this is, I want to look at this up here. This is something that's very elementary and you did it middle school. What happens when a solid melts?
It becomes a
It becomes a liquid. What happens when a liquid boils? It becomes a gas. Yes, what do you need?
Is 13,534 kilograms.
All right, so just give me grams. 13 point what? 13.5?
534.
All right, so multiply right now, somebody, right now. Write that down, write that down. Multiply that number times 0.76. Multiply that number times 0.76. I'm going to erase some of this stuff.
10.28.
What is it?
10.28.
10.28. So that's a little closer, right? So he said that the density of mercury,
13.534.
so that times 0.76 is going to be 10.28. Getting a little closer, yes?
5.
So that would be 102.8 kilopascals. So it's there somewhere, though it's 101.3. Yes?
When will you get sublimation? At what point?
All right, could you hold that question for a second? I'll get there. Okay. So, melting, evaporation. So that's pretty easy, right? There was a question here with sublimation. Well, every substance is different. Water will sublimate, will go from a solid to a gas at low temperature and low pressure. Yes? Carbon dioxide will go from a solid to a liquid, from a solid to a gas at room temperature and 1 atmosphere. So it depends. It's called, and we'll look at this, not today, but we'll look at this in another chapter, triple point diagrams, which will be able to tell you the conditions, Mustafa, that you need for something to sublime. And oftentimes it's rarely taught. What is the opposite of sublimation? It actually sounds like a legal term, deposition. So that's going from a gas to a solid is deposition. And sublimation is going from a solid to a gas. Easy? Yes? No big deal. And make sure you look at phase change from the other lecture. I talked about potential energy.
I have a question.
Okay, yes?
How'd you get deposition?
What do you mean, how did I get it? It's just the opposite. Like, how do I get...
Okay, water
If something evaporates, how does it condense?
it condenses.
Yeah, you just reverse the temperature. It's just, you're reversing it.
Okay.
Same thing with deposition with carbon dioxide. But you need those conditions. I understand that, and we'll talk about it. I don't really want to talk about that now, but there's a way you simply reverse it. These are reversible processes. Okay? They're reversible. Yes? Okay? I'm just trying to think of a chemical. I think caffeine will go from a gas to a solid at room temperature. When we were in college in organic chemistry lab, we did deposition of caffeine. I think we heated it to purify it. It sublimed and went to, I think, I don't know, I have to look at my notes. But anyway, deposition can occur. It's the opposite of sublimation. They're reversible physical processes, okay? We'll look at those more carefully when we talk about triple point diagrams. What, did something just happen? I heard a big ding. Is that still running?
Yeah.
It's still running? Okay. Now, right. So, I just want to talk about boiling and then we're finished. Okay? Boiling is a very simple process. Enzo, have you ever seen something boil?
Yes.
Yeah, you have. Matter of fact, you're kind of like spontaneously forming bubbles, aren't you?
Yeah.
Right? Well, if water is less than 100 degrees, right, that means the vapor pressure isn't strong enough to form bubbles. When the vapor pressure, do you understand what pressure is? It's collisions. The more I heat...
The particles collide with the surface of something?
Yeah, collision of particles. Let's just leave it at that. Just collision of particles causes pressure, right? So when I'm evaporating something, I'm causing a vapor pressure, a pressure caused by vapor. Does that make sense to you?
Yeah.
Yeah, just particles are being eaten off by the vapor, and the vapor is causing pressure, correct? And the pressure is going up, right? The atmospheric pressure is going down, right? Does that make sense? When the atmospheric pressure and the vapor pressure are equal, that allows bubbles to form. They'll just form in the liquid. And you know what that's called? Boiling. Now, let me ask you this. If I reduce the atmospheric pressure, does the vapor pressure have to be higher or lower for boiling? It has to be lower. So let me ask you a question. In Abu Dhabi, water boils at 100 degrees Celsius. We're at sea level. If I go up into the mountains of Switzerland, is the atmospheric pressure higher or lower there?
Lower.
It's lower. So does the vapor pressure have to be higher or lower?
Lower.
What's the relationship between temperature and pressure? The higher the pressure, the higher the temperature. The lower the pressure, the lower the temperature. So let me ask you this. Will boil, it's a direct relationship. Will water boil at a lower temperature or at a higher temperature in Switzerland?
Lower.
A lower temperature because the atmospheric pressure is lower. The vapor pressure doesn't have to be as high to be equal. The vapor pressure is controlled by the temperature. The higher the temperature, the higher the pressure. Gay-Lussac's law, right? If I go down to the bottom of the ocean and I can set up a laboratory and it's a lot of pressure down there, but I'm immune. It's a magic show. And I can set up a table and, and I have the pressure. And is the water going to boil at 100 degrees Celsius?
No.
No, it's going to boil at
A lot more than
a lot more than 100 degrees Celsius, right? You get it?
But water does boil down
Do you understand that boiling is where the vapor pressure and the atmospheric pressure are equal? I lower the atmospheric pressure. The vapor pressure doesn't... Can I create a situation in a laboratory where I can boil water at room temperature?
Vacuum pump.
Sure, yeah. I take what we call a bell jar. Okay. Can I erase some of this? I'll take a bell jar. I have a plate and a bell jar on top of the plate. And I have a hose that goes to a pump. And I pump out the air I have my beaker full of water, and it's going to boil at room temperature. It's really cool. You can boil water at room temperature. Is that boiling water hot?
No,
No, it's room temperature.
but it's still boiling.
Still boiling. Because the atmospheric pressure is way low. So do you see that I can control boiling by controlling pressure? Does that make sense?
Just because you're
Al?
controlling.
No. I ask a question. Does that make sense? Let me finish. Does that make sense?
Yeah.
Okay, good. So do you think, therefore, that I can control when water sublimes based on pressure and temperature? Does that make sense to you?
Yeah.
Yes, it does. When I did my research in undergraduate, in college, we had to sublime, we couldn't heat our solution to get the solute out of it. You know, you do this chemical reaction and you need the solute, but it's a solution. So we got to get the water out of it without harming the solute by heat, right? So what we had to do is we had to do something called lyophilization. Lyophilization is the sublimation of water, specifically water, from a solution. So we took our solution, put it in a jar, hooked it into a vacuum pump, put it in a giant barrel. The barrel dropped the temperature down below zero, reduced the pressure. You come back the next day, and instead of ice, a solid solution, you had powder. The water sublimed, went away.
But that powder, what is it made of?
Well, whatever it was, it's unimportant what the powder was, but we needed, you take a chemical reaction and it occurs in a vessel. And we needed whatever was in that vessel that's mixed with water. Correct? Well, we need whatever's in that water. We need it. So what we did was, we didn't heat it, we froze it, and then reduced the pressure. If you run a business and you have important papers, and the roof collapses, and all your papers are soaking wet, isn't it hard to take the papers apart? You're going to lose the papers. They're destroyed, aren't they? No, what you do is you send them to a company that will lyophilize them. They'll put them in a giant, they're not going to cook them because you're going to burn the paper. So they'll put them in a giant cabinet, lower the temperature, lower the pressure, and the water disappears. And you're left with the papers. And the papers, I have a video I can show you from YouTube.
Where does the water condense though?
Water's not condensing, it leaves. It's swept away. It's exhausted. The water evaporates. It sublimes into a gas. Then the gas is sucked out.
That's what I was asking.
Yeah, it's sucked out. Because the vacuum pump is sucking out the air. You suck out the air, you're reducing the pressure. You reduce the pressure, that anything is produced in that environment is going to be sucked out with the air in order to maintain the integrity of the vacuum. We're done, go to lunch.